All right, everyone, as always, thank you for joining our traffic flow webinar series. Today is my great pleasure to have my friend Vikash Gayah from Penn State University giving a very interesting talk on deep reinforcement learning and MFDs. Let me read you quickly his bio. So he's an associate professor in Penn State. He joined in 2012. He received both his BS and MS degrees from Central Florida University and the PhD from California, Berkeley. All right, so he serves in several editorial boards, including Transportation Research Part C and B, then IEEE System Magazine, and he is handling editor for the TRR and a member of the Transportation Research Board's Committee on Traffic Flow Theory. All right. He has very many awards. Gordon Newell is my favorite of your awards, and also the Career Award, very prestigious. All right, so without further ado, thank you, Vikash.
All right, thanks, Jorge. Appreciate that introduction. And yeah, so today I'll be speaking about application of deep reinforcement learning for perimeter metering control in urban networks with MFDs. I really appreciate everyone taking the time to join. Time is very precious these days, so an hour during the working day, is very significant. So thanks again, and I hope you enjoyed the presentation. So before I go on, I just wanted to acknowledge collaborators. So this work would not be possible without PhD student Dongchin Zhao. He is the main driving force behind this work. He's in attendance today. And so he will also field all of the most difficult questions. And so, but I wanted to acknowledge, this is more his work than mine. Also, just acknowledge NSF and the Penn State Institute for Computational and Data Sciences, which helped fund this research. So to get started, this is a traffic flow theory committee webinar. So assuming everyone is familiar with the concept of the MFDs, but just a quick summary. Basically, MFDs are tools that are used to simplify the modeling of transportation networks by aggregating vehicle behavior over large spatial regions. And so what we mean by that is, if we have a transportation network and we want to model the behavior of vehicles on this network, it turns out these are extremely complex. If I wanted to model this with a high degree of fidelity and in great detail, I would have to break this network into its component links and nodes, and then model the behavior either of vehicles on individual links or nodes, or the behavior of individual vehicles on all of these links and nodes. You can see here, this is downtown San Francisco. This is a very, very large task because there's like hundreds of nodes and many more links. So instead, one way to do this is we can look at the behavior of vehicles within regions of the network. So we draw a box or a circle or some enclosed space around this network, and we say that we don't really care about what's happening within the region at individual points within the region. We just want to know on average how this behaves. This is a fairly new paradigm, and it works really well when the region is homogeneous in both network structure and congestion, meaning similar streets throughout that region, and that congestion is more or less uniform around that, within that region. If that's not the case, then we can subdivide this network into subregions and then model the behavior within each of these regions. Now, this sort of strategy is only possible because we can use well-defined relationships between network productivity and accumulation within the regions to model the traffic network dynamics. So these relationships between vehicle productivity and accumulation or use has been studied for a long time, but it was recently that they were used to sort of identify a dynamic model that can be used to explain how accumulation or how congestion in a particular region will evolve over time. And so it relies on this notion of a macroscopic fundamental diagram, which is a relationship between density or accumulation, or how many vehicles are within each region on the x-axis here, and then the productivity of the region, something like a measure of flow, so how many vehicles are able to move on average on each link, or trip completion rate, so the rate that vehicles are able to complete their trip. We could also think about that as like the amount of VMT allowed during any unit time. And so on networks where these well-defined relationships exist, we can then take this network, this complicated network, and simplify it into just a handful of regions and just model the number of vehicles that go from one region to another and the evolution of the number of vehicles within each region over time. That's sort of the quick summary of sort of the macroscopic fundamental diagram framework. Now, these types of frameworks have been used to develop different types of control strategies in the literature. So one would be congestion pricing. We're going to charge a fee for vehicles to enter a specific protected area of a network or a protected region. And so, researchers have used the MFD framework to sort of set these prices. It's been used for space allocation. So basically, how much space to assign to cars versus transit within a region. This figure doesn't mean like the left-hand side is for cars and the right-hand side is for transit, but on average, what's the split between road space dedicated to cars and road space dedicated to transit, assuming that this road space is, again, homogeneously distributed in the region. Some researchers have used this for street network design to answer questions like, should we use one-way streets or two-way streets? And it turns out MFD frameworks can help answer that question. It's also been used for large-scale vehicle routing. What I mean by large-scale is not specific links and nodes or specific paths, but paths on a regional level. So if I am a vehicle somewhere in region 1 and I want to go somewhere to region 5, I have a couple different options. We can use like sort of like a large-scale or a regional level routing. So these are just some of the strategies that have been used, but the most prevalent or the most notable is perimeter metering control. And so the idea behind perimeter metering control is we want to limit how many vehicles or the rate at which vehicles can enter a specific region in the network. And the idea for doing that is if this region gets too congested, we've seen with the MFD that the more congested the region gets, the less productive it gets. And so if we can find a way to limit how many vehicles can enter that network, we can keep the congestion level relatively low, and we can maximize the productivity of vehicles within that region. The idea then is to, the vehicles that would have instead entered, we sort of force them to wait somewhere else where they might be less damaging to the overall network operations. There's a lot of literature on perimeter metering control since, over the past decade or so, since the MFD has been, seen its resurgence in the research literature. So I'm just going to go through some of them and talk about the issues that we are trying to tackle today. This is not meant to be like necessarily criticisms of these methods. They're good. It's just sort of things that we would like to try to address in our work. So the most common state-of-the-art method for MFD perimeter metering control is model predictive control. But the problem that we see with the model predictive control is it requires pretty accurate knowledge of these models that govern traffic dynamics. So the rules that say how many vehicles are going from one region to another and the dynamic equations that govern that process. As a part of that, it requires full knowledge of the network's MFD. So we need to know the functional form of the network's MFD. There are other methods like feedback-based methods and also like optimal control methods. These also require full or limited MFDs. So we need to know what that flow density or productivity accumulation relationship is. With the feedback-based methods, we also need to determine ahead of time what level of congestion we're trying to achieve, which is like a set point. And then what the feedback-based methods does is if the level of congestion is greater than that amount, it tries to limit it. And if the level of congestion is less than that amount, it tries to allow vehicles to enter that region. But it has to be determined a priori. So we have to tell those methods, this is the level of congestion we think is most reasonable. Recently, there's been a model-free iterative learning approach to perimeter metering control, which does not require knowledge of the MFD, but it still requires an estimate of that set point of congestion. essentially the critical accumulation or the critical level of congestion that maximizes productivity. So all of these require a lot of detailed information about the MFD in the network. Now, this information turns out to be not so easy to obtain practically. Now, there have been a lot of studies that have talked about using MFDs and even how to estimate MFDs with different data sources, but they generally come from simulation world. The fact of the matter is we don't have a lot of empirical data or empirically estimated MFDs. Relatively few studies in the research literature actually have these empirically estimated MFDs. And in fact, MFDs, to my knowledge, have not been used for any real control purposes in practice because of the difficulty in obtaining them. And then sometimes these MFDs are subject to like the relationships that are not really well behaved, not really well defined. There's a lot of scatter, hysteresis type phenomena. And so then, identifying that set point or the critical accumulation becomes really difficult to do. So with all that said, the purpose of this research is to use a model-free deep reinforcement learning approach to tackle the perimeter metering control problem. And the goal here is to develop a perimeter metering control method that requires no knowledge of the MFD or underlying traffic dynamics. Okay, so again, we do not need to want to know the MFD. We do not want to know in a multi-region network what are the equations governing how vehicles move from one region to another. We're trying to say that's unknown to us. It might be a messy process. It might be a simple process, but we're trying to learn that process through deep reinforcement learning and use that information for perimeter metering control. And then, given that goal, we want to develop a method or a solution to the problem that is stable, so that it's robust to different environmental scenarios. And what we mean by that is, are these relationships well-defined, not well-defined? Do we know the demand well? Do we not know the demand well? It should work under all of these environments. We want it to be effective. And so by effective, we mean compete with the state-of-the-art methods. In this case, we use the MPC method. We want it to work just as well, but again, require less information. And then we want it to be transferable. So if we develop this model for a particular situation, it should then be able to be transferred to other situations that it was not developed necessarily to tackle. So with that, next I'm going to go through just a quick description of reinforcement learning. Again, I'll leave all of the tough questions to Dongchin. So for those of you that don't know much about reinforcement learning, and that included me not too long ago, in reinforcement learning, what we have is an agent that's going through a process of sequential decision making decisions, learning about the consequences of the decision, and then using that to inform future decisions. So we have an agent. This is the controller. This is the agent is what's going to make the decisions. We have an environment. The environment is reality. And so the agent receives some information about the environment. We call that the state. So it's not everything, but it's a subset of information from the environment. Using that state as an input, as a snapshot of what's going on, the agent makes a decision that will impact the environment. So he takes an action. In this particular case, a control action. Of course, that control action then changes what happens in the environment. And then based on that change, the agent receives some information about that change, and we call that the reward. So the agent gets a reward for its actions, and the agent then sees a new state, makes a new action, and then gets a new reward. And it does this over and over again until the agent learns what's the best action to take that will maximize my reward. So the goal here from the agent is to select actions that maximizes the total reward currently and considers what the rewards might be in the future. Now, the future rewards are discounted. So the agent cares more about what's going to happen in the immediate future than what's going to happen down the line. But he does consider what's happening down the line, and so he doesn't lead the environment to a state that might be not so beneficial in the future. The agent learns by trial and error at first, so tries a lot of different things, to figure out what the optimal trajectory that it should follow in terms of its decision making. And at first, these decisions are random. So the agent will make some random decisions. It doesn't know what to do. It doesn't know anything. So it says, let me try this. Let me try that. It learns from these actions and then starts to make more informed or better decisions over time. So I'm going to demonstrate how this might look like for perimeter metering control, just a single region of a network. So one region here. Okay, so we're actually going to talk about the results for a two region, which is much more complicated. But in a single region, we can just use this as an illustration. So let's consider here a congested scenario. I have here an MFD, so productivity of the network, accumulation of the network. It's in gray. That represents like we don't know what that is. It's just there. The agent has no idea about this information. There's some state that the agent is, that the environment currently is in. So the agent receives information about this state. It says, hey, we're at an accumulation N1. The agent will then make a random decision. In this case, let's assume that the agent says, we're going to make this less restrictive. We're going to allow more people to enter this region. Well, if that happens, the network will get more congested. If it gets more congested, you can imagine that the productivity will go down. So that happens in the environment. The agent only then receives information about this reward, R. So it just learned that, hey, we're at state N1. I made this action, the specific action to ease off the restrictions, and I received this reward R. Okay? Maybe that's not good. So the next time this state happens again, the agent makes a new action. He says, how about let's try making this more restrictive? Let's limit the number of people that come inside the network. It turns out in this case, the region gets less congested, and so the reward that the agent receives is higher. And so now the agent learns, hey, if my state is at N1, I generally want to make the control more restrictive and let fewer vehicles into this network. We can see the same thing in an uncongested scenario, right? We start off uncongested, a state N2. The agent knows, okay, we're at a particular state N2. We try something, let's make it more restrictive. If we make it more restrictive, fewer people enter. The reward is fairly low. Next time we try it again. We ease off the restrictions. We get a reward. That reward is high. And so the agent says, okay, if I'm at a state N2, I want to make the control less restrictive. I want to let more people in because that's going to increase the productivity of this network. And so then over time, this process repeats itself for a variety of states. And the agent essentially learns that, given these states, what I really want to do is I want to move towards this particular point, which again, the agent does not see the whole MFD, but he learns that this critical accumulation is where I want to be. And I'm going to try to move to that, which is essentially in a single region perimeter metering control, we know that's the optimal solution. That's what we want to do. So that's sort of a demonstration, like a graphical demonstration of how this process works. Now, we're going to consider a more complicated case where there's a two-region network. Traffic dynamics are governed by well-defined MFDs. Here are the dynamic equations. This is a visualization of the process. And just to remind you, the dynamic equations here and the MFD, we're going to know what those are in the numerical simulations that are going to essentially represent the environment. So this is what we're going to use as a simulation of reality. But these are unknown to the DRL agents. The DRL agents has no idea about what's happening behind the scenes. Okay, we have an inner region, R2, which is going to be assumed to accommodate fewer vehicles than an outer region, R1. They have different MFDs to make it even a little bit more complicated. So the MFDs within each region are not the same. They're scaled differently, okay? And we're going to simulate in these experiments a morning peak period where there's a high demand of vehicles going from region 1 to region 2. So you can see here a big peak of vehicles going from region 1 to region 2. This is essentially a morning peak period with more vehicles traveling from an uncongested periphery into a more congested city center. On the right-hand side, we show the accumulations under no control. And in the no control case, what you see is we have the accumulation for R1, the accumulation for R2. Essentially, under no control, region 2 gets very, very congested. Region 1 is not very congested, even though Region 1 starts out more congested than Region 2. The demands push the accumulation in Region 2 up, push the accumulation in Region 1 goes down. And so in the end, if we do nothing, we get a lot of congestion in the central portion of the network, little congestion in that periphery, and overall that leads to low productivity of the entire network. So to make this even more realistic, in our simulations, we assume that there are both errors in the demand and the MFDs. So what we mean by that is there's a demand, an average demand. So the demands that we showed are in this black line here. But the actual demands that happen during any instance are equal to that estimated demand, but plus or minus some error. Okay, so the dots here kind of show what the actual demands might look like compared to the average demands. And so you can see it can fluctuate significantly. That fluctuation is proportional to the estimate of demand. Essentially, if the demand is small, we would know that with more certainty than if the demand is big. There's just more opportunity for error, which I think is a realistic assumption. But you can even see here in the demand for region 1 to 2, there is quite significant error here, so it's kind of realistic. We also assume there are errors in the MFD. So we assume that the MFD had this nice line in a linear, this nice well-defined relationship. Well, the actual MFD can differ significantly from that average or that well-defined relationship. So we included scatter in the MFD as well. The scatter in the MFD is proportional to the accumulation in the network. So higher accumulations have more error, which is consistent with everything that we know about MFDs. They're less well-defined in congestion than they are in free flow. So again, it's kind of mimicking what we know to be true. And so we trained a couple different RL agents, DRL agents. This is everything I show you in this presentation is the result of 2 different studies or papers that we've been working on. So in one of them, we used a discrete reinforcement learning approach. In this discrete approach, our state, what the agent knows about the environment, it knows the accumulations in the region. It has an estimate of the demand, which again is not the actual demand, just the estimate of demand, and the actual demand is subject to includes that error term, and it could be significantly different. And we also assume that we know the previous control action. In the discrete RL, what we do is we take our control space. In this case, we have a controller that has a minimum value and a maximum value, and we discretize the set of control actions to reduce the computational complexity, because in this particular case, we used a deep queue network approach that can only consider discrete actions. And to make the problem more solvable, what we did was, when we know what that previous control action is, so if this is the previous control action here, the next control action could only be one of the adjacent or the current action. So if I'm at this particular control point, I can stay the same. In the next time step, I can increase the controller or I can decrease the controller, but I can't jump from here all the way to the maximum. This has an added side benefit of just sort of smoothing out the control over time. So it might be a little nicer for implementation. We just don't go from like a completely open network to completely closed right away. But it also is more computationally effective, which is very nice. And we also considered a continuous reinforcement learning agent that, again, instead of a discrete action space, we looked at a continuous action space. So we have a minimum and maximum control value, and consider that the agent can take any specific value within this space. This was a more advanced approach. It turned out to work nicer. It has the same states, the accumulation and estimate of demand, but because of the continuous space, we actually did not need to know anything about the previous control actions. In both cases, the reward that the agent receives is the trip completion during the current time period. So when the agent makes a decision, it knows how many vehicles completed their trip during the previous time period. Here's where I'll pause and say, in reality, we probably will not know that information. If you ask me to go into any network and say, how many vehicles completed their trip within the last 5 minutes, there's no way we can estimate that, I think, with a great degree of certainty, unless every single vehicle was monitored. That being said, we have surrogates that can tell us the exact same thing. If I'm looking at trip completion rate, we know that that's proportional to the average flow of vehicles in the network. So all we simply need to do is measure the average flow, which we can do with a set of detectors, and we can use the average flow as a surrogate for this trip completion rate as the reward. And so that actually makes the applicability of this approach much higher. It's fairly easy, or much easier, to measure the average flow in real time on a real network than the trip completion rate. Just for the purposes of our numerical simulations, we use the trip completion, but I think essentially it's the same thing. So we compared the DRL agents with a couple different approaches. We have the no control case where, I think I already showed you the results for that. There's no limitations. We assume that there's absolutely no control. The vehicles just do what they will. We compare with the model predictive control. Again, this is the state-of-the-art method. It requires information about the MFD, the demands, and it's an optimization-based approach that essentially looks over some prediction horizon and optimizes the control actions in the near future, and then only implements the most immediate actions, and then repeats this process over and over again. And again, we have the two RL agents, the discrete RL and the continuous RL. And again, more details, we can talk about that later. So to the results now, the training of both reinforcement learning agents is very stable across different levels of uncertainty and different levels of uncertainty in the demand and the MFD. So what I'll do now is I'll show just one picture here. This is the training process. This represents a training process for the reinforcement learning agents. The green is the discrete version. The blue is the continuous version. The gray line here represents the trip completion, or the total number of trips completed in the no control case. The orange line represents the total number of trips completed in the MPC case. So you can see in the MPC case, if I apply some control, we do a lot better than when there's no control, which makes sense, obvious. And so the RL agents, we show kind of two different things. We have a line and we have a shading. The shading represents a range of outcomes. So basically, each of these agents requires some sort of, it's a stochastic process, the training of these agents. As I mentioned before, they make decisions at the beginning purely randomly. And so those initial random decisions can change how well the agents are able to learn or converge to a final outcome. So the shading, the bottom of the shading represents the worst trained agent that we did. The top represents the best trained agent. And the solid line represents the median case. And so what's really important is that regardless of the initial starting points, the agents tend to always converge to a very high value, which is great. Okay. In general, at first, both reinforcement agents are worse than the no control case. So each point on this line represents like an iteration of the learning process. We could think about it as like a day. In reality, we make decisions on the first day, and this is what happens. So in the first day, things are really bad. It's actually worse than the no control. And we might think like, well, why is that? Like, it should not be worse than no control. And the reason for that is, well, the reinforcement learning agents are making decisions randomly. So I have a 4-year-old son and a 2-year-old daughter. If I had them just randomly pick the control actions on a day, they'd probably do pretty poorly. So it's a random process, but over time, over some number of days, the agent starts learning. And so the initial process is just an exploration process. I'm randomly doing things and learning from it. And then after a while, the performance of the agent starts to increase. That's the learning. So we have the exploration, and then we have the learning process where the agent's learning, okay, I need to learn from the actions of my consequences, and then starts to make better actions in order to get better consequences. So what we find is that the green, the discrete reinforcement learning agent, actually remains, the performance is really poor for a very long time. And then it starts to pick up. And once it picks up, it gets better than the no control case, and it actually starts to approach the MPC. But it takes a while. Okay, it's good that it's learning. It's trying. But you really don't want to be in this network for the first few days because you're doing worse than if this thing wasn't here. The continuous reinforcement learning agent, though, the blue picture, wow, it learns fast. This guy is much smarter. He starts off really poor, but then very quickly, is superior to the no control case, and then he starts getting smarter and smarter, and eventually, the continuous reinforcement learning agent actually outperforms the MPC, which is very interesting. Now, it should be noted that in MPC framework, MPC is an optimization process, and so you can play with the parameters of the MPC to improve its performance, a little bit. But the more you play with that performance, I mean, essentially you're changing things like how complex the optimization problem is, the harder it is to solve that optimization problem, and it's not guaranteed to be, a lot better. So even though the blue line is better than the orange line, I think it's not necessarily that it's better, but it's comparable. Our deep reinforcement learning agent the performance is comparable to the MPC, even though the deep reinforcement learning agent knows nothing about the MFD. It knows nothing about the system dynamics. It's just learning that. While the MPC, we had to tell it, here is what the MFD of this network looks like. Here is what the system dynamics look like. So this is trained under one level of uncertainty for the demand and one level of uncertainty for the MFD. In this case, it's actually no uncertainty, okay? We've tested this for a range of uncertainty values. So as I move from left to right here, I have more uncertainty in demand. And then as I move from top to bottom, I have more uncertainty in the MFD. As the uncertainty in the demand in the MFD increases, because it's a random process, the no control case now has a range of outcomes, and the MPC now has a range of outcomes. It's no longer one value. But what's important is that consistently, the deep reinforcement learning agent, the discrete version in green and the continuous version in blue, learn, and they learn to basically get very, very close or even get better than the MPC agent. Again, without actually having any information on the MFDs. The green lines were only trained on some of these options. Again, this is the result of different papers that we just sort of put together for this presentation. So there's no reason that the green line is not on this figure other than we just didn't do it. But it could easily be added. And the second thing is, so both agents are working well, and the continuous reinforcement learning agent is doing even better than the discrete agent. We're showing here some just the actual accumulations within the network for some of the different cases. So again, the no control case, the MPC case, deep reinforcement learning discrete case, and the reinforcement learning continuous case. Essentially, all we wanted to show is that, remember, the region 2 under no control gets very, very congested, and region 1 was very uncongested. But when we apply any sort of control, either the MPC control or the deep reinforcement learning agents, they all sort of figure out that, listen, we really should make sure region 2 does not get congested. That's, which is exactly what we would expect, right? We would try to keep that accumulation close to the critical accumulation. So this is this red line here, again, unknown to the RL agents, but I just superimposed it. This red line represents the critical accumulation associated with the maximum productivity of that region. And so all of the control options here sort of realize that we need to kind of hover around this value. It doesn't matter if this one gets congested but it shouldn't be uncongested. We should sort of increase the number of vehicles in that particular region. We can compare the control actions, okay? So the orange is the MPC. At first, the MPC implements really strict control, so it closes off region 2. It relaxes that, and then it slowly closes it off again, only to relax it again. So it kind of like goes up and down a little bit, okay? It has good performance, but that's just what it looks like, the control actions. The discrete agents kind of mimics that, but in a really poor way. So it closes off region 2, which is great, and limits people entering it. And then it backs that off, and then it just sort of opens it up gradually. So it's a little bit different approach, but again, this is what it had learned to be sort of the best option. The continuous reinforcement learning agent sort of mimics the MPC. It's just not as drastic. So it does not completely close region 2 ever, and it does not completely open it ever. It just sort of kind of hovers in the middle, but we can see some sort of closure, a little bit of relaxation, again, closing it back again when the congestion starts to build, and then relaxing those constraints, that closure again. So we wanted to test sort of the performance, and here, so basically we looked at the cumulative trip completion of each method at convergence. So this is sort of like when the reinforcement learning agent figures out, okay, this is what I'm supposed to do. I'm ready. You know, it's showtime for me. We compared their performance at that showtime. The key thing here, no control. Our values are really small. So fewer trips completed than the MPC, DRL, and CRL. They basically increase the amount of trips that can be completed, which is exactly what we expect. So there's no surprises here. If we compare the MPC and the discrete version of the reinforcement learning approach, we see that the discrete reinforcement learning approach is just about 1% worse than the MPC. So it does worse. It's not as good, but it's actually close. It's pretty good. And remember, it knows nothing about the MFD. It knows nothing about the dynamic equations, whereas the MPC has to know that information. So, you know, without knowing anything, it's actually doing pretty well. It's doing almost as good as the MPC. When we compare the MPC and the continuous reinforcement learning agent, again, now the continuous reinforcement learning agent is surpassing the performance of the MPC. Okay. Again, we can optimize the parameters in the MPC, but I will say there was one other sort of model-free learning paper, and they have also found that in an iterative learning approach, they use iterative learning, we're using reinforcement learning, you can get performance that is better than the MPC. So this is not atypical that we can exceed the performance of the MPC. Now, the next thing I wanted to show was, is this thing really working? I mean, it seems to work, but does it make decisions that make sense to us? So what we did was we said, well, what would happen if the demand was so low in this network that you would never want to implement any control at all? Could the deep reinforcement learning agent figure that out? And it turns out, so this was our original demand. We just made all the demands really small. So no region ever gets congested, right? There's no congestion. The best thing to do is to leave everything alone and set all of our control actions to the maximum value of 0.9. So we tried that, and it turns out the continuous reinforcement learning algorithm basically figured it out. It learned what to do. Again, without any dynamic equations, without any knowledge of the MFD, it basically figured out the exact solution as the MPC. So, well, that's good. It gives us a lot more trust in it. We said, well, what happens if it's really congested? What happens if the demand into region 2 is so high that the best thing to do is just shut it down, stop vehicles from entering region 2? Can our reinforcement learning agent learn to do that? I don't think it would be any surprise to you what the answer is. It certainly did that. It learned that the control, the control parameter from region 1 to region 2, we should make that as small as possible to restrict any vehicles moving from region 1 to region 2. And when doing that, it has the exact same answer as the MPC. So we saw that it outperformed the MPC in a sort of a hybrid approach where we didn't know the answer. We've confirmed that it gets this exact same answer as the MPC when we do know the answer, so we can feel pretty good about its performance. Now, the next thing was, we examined we trained these agents in different environments with different levels of error in the demand, different levels of error in the MFD. And so we asked, well, what happens if we take one of these agents and then apply it to a different scenario, transfer it? It was trained in a low demand state, but a low error in demand state, I apologize. But now demands for some reason have a lot of error, it's more fluctuating. How well will this work? And so what we did was we tried to examine the performance of these agents in different scenarios with different starting accumulations, different demands, different MFDs, and different errors in these values. I have some pictures here, but I'll just sort of, I think, just save time for questions and things like that. I'll just sort of, go a little faster. But what we found is we compared the performance of our agents in different, again, applied to different environments. Okay, so the different environments are shown here, the variation and initial accumulation. Those are environments that start out with a different initial accumulation than what the reinforcement learning agent was trained on. So the reinforcement learning agent was trained always assuming, we have a specific level of congestion to start, and now the level of congestion is different, okay? And what we find is there's a wide range of values where the reinforcement learning agent still outperforms the MPC, even though it's not being applied to the scenario it was trained on, okay? So it just sort of demonstrates its transferability. Now, there is a range where it does not outperform the MPC, I apologize, where it does not outperform the MPC. So it is transferable, but it's not transferable, just to completely, absolutely different environments. It's transferable to environments that are close to the one it was trained on. In this particular case, when the initial accumulation is a little less than what the agent was trained on, or if it was a lot more than what the agent was trained on, it performs better than the MPC. When the initial accumulation is a lot less or a lot more, it's not shown here, but you can see these curves bend down. So eventually the MPC does better. So when it's a lot different, the MPC does better. But remember, the MPC knows what these new starting accumulations are. Our agents do not. We tried this with variations in traffic demand. So the amount of error in the traffic demand, again, we see the same sort of pattern. There's a range here. Again, all of these curves will eventually bend down. It's just not shown because the numbers were really, really high. It'd have to be like a huge variation in traffic demand increase, right? But even still, there's a significant range where our agents outperform the MPC. And we also tried with MFD modeling errors. So how much error in the MFD? Maybe we train it where the MFD has a particular level of error or a particular amount of scatter, and then we apply it in a situation where it has more or less scatter, or in this case, actually it's the entire range of the MFD. Is the network more or less productive? And again, there's a range where our agents do very, very well, better than the MPC. There's a range where they do not. So I talked quite a lot, okay? But in summary, we have a model-free deep reinforcement learning approach that appears to work well to solve this perimeter metering control problem for two-region networks. The methods are developed using both discrete and continuous action spaces. They are stable, meaning they converge always under different uncertainty levels and different measurement errors. So for all of the tests we did, they always converge and find what that optimal solution is for the agent, or an optimal solution, I guess. They're effective in the sense that when we compare them to the MPC, the performance of these agents are either comparable to the MPC or sometimes outperforms the MPC, even though the MPC has full information on the system dynamics and the MFD. They are transferable. They generalize well to unencountered scenarios. And just a general note for implementation, again, we train these agents assuming that the reward was the amount of trips that were completed during any time step. In reality, we don't know this information necessarily, or it might be difficult to obtain. However, we can easily get that information or a surrogate for that information in practice, because we can easily measure average flow in the network, which can give us a pretty good idea of what that trip completion rate is, since average flow is proportional to the trip completion rate. We can also use a subset of vehicles. If we had probe vehicles, we can measure just the probe vehicles and do the same thing. So there are ways that we can actually implement this in practice. And what we're doing now is working on, well, how can you develop this in a simulation environment and then actually go out and apply it so that for the first few days, you don't do a little bit worse than the no control. That would be the worst, is like we go and try to apply this and it takes too long to learn. Now, with the discrete reinforcement learning, that could be an issue, but as we've shown in the continuous case, it learns really, really fast. So we can feel pretty confident that it will do well. So with that, I guess I can take maybe questions, or I'll hand it over to Jorge.
Thank you, Vikash. Such an interesting presentation. Yeah, so everybody, you could unmute yourself so you can type a question in the chat. Well, I see a question right here by Bayer Abdullah. What is the control action to limit the flow at the perimeter? Are you using signal control or assuming congestion pricing?
Yeah, that's a great question. In this work, we were using numerical simulations. So these numerical simulations do not actually specify what the mechanism is that limits the vehicle moving from one region to another. This can be done in many ways. You can implement that using traffic signals and changing the signal timing from in the perimeter from one region to another. That's actually why the control actions aren't limited from 0 to 1. If it was 0, we would say we absolutely do not let anyone into this region. That's not practical. If there was a signal there, people might run the signal or whatever. So, we don't really specify what that is, but we can use signal control. You can use pricing. In some cases, I believe you can use variable speed limits. I mean, there are different ways you can do this, and that's been sort of practical implementation of that has been studied a lot by colleagues in the research literature. We just assume that in these numerical simulations, we're just saying that it can be implemented in some way. Thank you.
All right, we have another question by Hao Zhu. Oh, he's my student. Hey, Hao. Great work, thanks. In perimeter control, we assume some vehicles can't wait somewhere without damaging the network. It seems to require enough storage of some streets to accommodate them, and of course, a non-uniform OD. Do we assume the streets outside the region have infinite storage capacity? If not, how do you think we should balance the queue inside and outside of the region?
Yeah, so I mean that's a great question. If I had a single region and vehicles were maybe I can see me here. I don't know if you can see me or not, but if I had a single region, right, the vehicles have to come from somewhere, and that's outside the region. And so most single region perimeter control problems assume that those vehicles are waiting outside, there's infinite space, and those vehicles do no harm. Okay, so that is the single region case. In our case, we have two regions. So we have one region with another region around it. There's nothing that's coming from outside that. Everything is internal to this two-region network. So vehicles either start in region 1 or start in region 2, and if they want to go from 1 to 2, that they have to wait in the region they're in. So if I'm a vehicle and I'm in region 1 and I want to go to region 2, if I am waiting, if I am metered, I have to wait in region 1. Okay, so in that case, no, there is not infinite storage capacity. There's only the capacity of how many vehicles can physically be in region 1. So there's no infinite storage capacity. Actually, that capacity is very much limited. Okay, so if it considers the negative effect of vehicles waiting, and that's why when we have those examples of that in not the extreme demand cases, but the more general demand cases. That's why the optimal solution was never to just stop everyone from entering region 2. If we did that, they would just sit in region 1 and actually cause more damage than if they were to be allowed in region 2. So they wait in region 1, but the impacts of their waiting in region 1 are accounted for. Does that answer your question?
All right, it looks like it did. Another question by Bayer Abdallah. You showed that you protected the inner region and reduced congestion, while the outer region got a bit more congested. Wait, a bit more congested. Yeah, as can be expected. Sorry about that. What is the total net effect? Did you show that?
Yeah, so all of the results presented here are the total trips completed in the entire two region network. So it looks at the impacts both to region one and region two. So if we're limiting vehicles going from one to two, the results, all of the final results show that combined impact. So our agents are actually learning about the combined impact of these decisions. They're not ignoring the negative impact that occurs by making someone wait somewhere else. They're balancing that negative impact by making them wait with the positive impact by the reduced congestion that we get in region two. So that balance is absolutely considered in all of the cases, the MPC and the deep reinforcement learning agents. And essentially the no control case, which is a type of control, but it's just doing a specific action. So yes, the short answer to that question, we absolutely consider that. All of our results consider that. And the final result is by taking these control actions, we can actually make things better for the entire network. Will there be some individual vehicles that are worse off? Probably. But overall, everyone is much better off.
All right. A question from Zaid Khan. Thank you for the talk. Can you share a little more details about the DRL model?
Absolutely. I think what I will do is I will pass that off to Dongshin. Would you like to provide a little bit of details? Well, I guess, Dongshin, are you there? All right,
I think,
no worries. So basically, we have a couple different types of reinforcement learning agents. In the discrete space, we did a deep Q network. It's basically a single neural network that is both trying to assess the impacts of the actions and decide the next actions to take. For the continuous space, we did a DDPG algorithm. This essentially with an actor-critic method. So they're basically two neural networks. One neural network is deciding what action to take. The other neural network is sort of evaluating the decisions of those actions, and they work together. These are actually pretty standard, mechanisms in the reinforcement learning literature. We didn't really develop any specific techniques for this problem. We were just applying them to this problem. So I hope that answers your question.
Vikash, and what about the input to that neural net? You mentioned is the accumulations, right?
Yeah, so the states in both cases included the accumulations and an estimate of the demand. That is it. So we have an estimate of the demand, which I mean, in general, we should know for any network about, a high level estimate of the demand, particularly on a regional level. And we're assuming that we can monitor the level of congestion within each region at any point in time. That was a little trickier, but again, we can do that even with detectors. We can sort of use that information to say, you can use it with probe vehicles and estimate average speeds. There's a lot of ways in practice to estimate this. We're assuming that these are sort of the information that's available. I will say there's a lot of literature out there, particularly on the perimeter median control problem, optimal control, feedback-based methods, the MPC methods. None of our inputs are any different. Actually, it's a lot less. We don't even need the MFD.
Right. So, but for one region, all right, so the input to that neural net for a particular region, so it's going to be the accumulation in all the regions and the demand from all ODs?
So yes, so the accumulations are the accumulations within each region that are destined for another region, and the demand from one region to another region. So it's the accumulations and the demands stratified by OD. Again, I think that's fairly typical of MPC-based controls.
So there's two matrices that are input to your neural net then.
Correct. In this case, there were 8 data elements because we had 2 regions. Nice. So a 2x2 on the accumulation side, a 2x2 on the demand side.
Right. Interesting. All right, let's see. We have another question by Parth. Nice presentation. How are the size of the regions decided?
Yeah, in this particular case, honestly, we made them up. We just said, hey, we're going to have a small region, we're going to have a big region. There's absolutely no rhyme or reason for that. I mean, the MFDs that we used were generated based on, or were obtained from real MFDs. So we basically used the MFDs of Yokohama, Japan, and we scaled them up or down to say, here's a big region, here's a small region. You know, I don't have a good answer for you other than we created a scenario that we thought was realistic, but we don't think the results hinge upon, the size of these regions.
Right.
In practice, you'd go and look at the network, you draw, circles around them and decide, what that size is for that network.
All right, another question by Tinan Lee. Thank you for the nice presentation. That was very informative. However, the claim that RL doesn't require full MFD information seems a bit tricky. You do require a simulation to conduct RL, right? Could I assume
Yes.
that the simulation is built upon the knowledge of the MFD?
So that is a fantastic question. Okay, in our simulations for this study, we have an environment. Now, I would love to go outside and convince New York City to say, hey, would you mind if I train this DRL agent on your network? They will not let me, right? So we had to conduct these experiments synthetically. That being said, you are right. If we're training these agents in simulation, then we would have to have some information, and that information would be enough to estimate the network's MFD. And so, yes, we can say that we have enough information for the MFD. A question would be like, why don't you then use that information? And the answer to that is, you're right, we probably should. Okay. However, this agent is developed in a way that if New York City did decide that I was, that they made me, Vikash Gayah, czar of traffic control in New York City, we can implement this agent and we don't have to estimate the MFD. Every single day, we would allow this agent to make some changes and we would just monitor what's happening on the network. Like I said, we can monitor the flows. Okay, we would monitor that. We don't need the same information that we would need to estimate the MFDs. We would just monitor how the traffic situation changes in response to our actions. In that case, we do not need the MFDs. We measure this, and what we've shown is that if that were true, our agent can still converge upon a solution that would provide beneficial control. So the idea was we wanted to come up with an agent that would work in practice, assuming that the MFD information was not available. In order to test that, of course, we have to create an environment in which we know the information, but we never give that information to the RL for the purposes of this test, simulating a realistic scenario in which we do this in practice, but we never give that information to the RL agent. Did that answer your question? I think it's an excellent question, and it's something that I probably should have made more clear.
Yeah, I think it's probably because the confusion of model-free, the concept, and RL, it means a different thing than, I guess, in other areas. Right, we still need models, right? It's just we're not.
Yeah, I mean, well, we need models to test things, but I think this can be implemented without any knowledge of the MFD or things like that, as long as we have those particular input informations that are required. And we will do more general testing. This is Dongchen. I did mention he's a first-year PhD student. This is the work that he did in just his first year, so I'm very excited for the work that he's going to do to follow, because I think he's going to take this and just keep building upon it. I think there's a lot of areas we can improve, even though the results of this are very good.
Yeah, it's very impressive. So Vikash, if you have more time, there's a couple more questions there.
Yeah, sure.
All right.
I can read them. How long is one step in the reinforcement learning to collect the reward? Our time steps were of, I think, 1 minute. Our simulations were for an hour. The time steps were for 1 minute. Why does the discrete Q-learning method, is very slow to learn at the beginning? Is it possibly due to the constraint on the adjacent action space? Yes, we believe that is the case. The good news is it was eventually able to learn, but it took a little while. what if we allow the discrete actions to jump? We can definitely try that. We've tried it to some degree and we've had some success. We found that the continuous action space was actually more profitable. So I wouldn't say we abandoned the discrete action space. That was our first attempt. The continuous was the second attempt. I still believe the discrete action space can be improved upon. We just found really good results with the continuous, and so we sort of moved in that direction. But I don't think we're done with that. Will it still be able to converge? I think the short answer is it's promising. I can't give a yes or a no, but I think it's promising that we can make some adjustments to make it more flexible and still do better. The question would be, why continue with the discrete action space if the continuous action space is working so well? The discrete action space necessarily provides limitations, but if the continuous action space is doing better and is able to be trained, and we know it converges, we might just want to keep with that. So I guess that's a long answer to the question. And then I think Parth had a question, in a realistic setting, how could the state be created based on the information available in the real world? That's a great question. The demands, I think, are something that we can know. I think, no traffic engineer designs a control strategy without having some information about the demand. Now, in the real world, with like in microsimulation, or our demand matrix is huge. We have like thousands of origins, thousands of destinations. In a regional MFD type of model, you really just need you have a handful of O's and a handful of D's, and so it would be very, very possible to estimate those demands. So that one, I'm just going to wave my hands and say that's doable. The tougher one is the accumulations broken up by destination within each region. We can certainly get the total accumulation or an estimate of the total accumulation within each region just using detectors, occupancy associated with density, associated with accumulation. So that part's easy. The trick is then breaking up that accumulation by region. I think we can do that by combining information from detectors and probe vehicles. If a subset of vehicles are probe vehicles, it can give us an estimate of like the split of the vehicles in region 1, how many of them are generally going to region 2? Okay, that information can be used to then take our accumulation information and split it by destination.
Yeah, like historic data. Also.
Yeah, so I think there's a lot of different ways we can do that, historical, real time. So there's certainly going to be some positives and negatives, and those can be things that we look into more in future work.
But do you really need those accumulations like that? Did you try not including that information in the state space?
Let us write that third paper, Jorge, and we'll get back to you.
Yeah, because sometimes, the neural network might not be sensitive to those, right? Yeah,
so I guess the short, without giving too much away, I'll say that I feel like it's very possible to do that. And then our method would require even less information than sort of the MPC type method.
Yeah, the less you need, the better, right?
Yep. So we already don't need the MFD. If we can get rid of that destination-specific accumulation, we can do even better.
Right. So excellent. Very good work. Very good questions. Thank you, everyone, for your participation. Thank you, Vikash, again.
Thank you for inviting me, Jorge, and everyone. Really, this current situation. I hope everyone stays safe and healthy. And I know how valuable an hour of your time is, so I really appreciate it.